The room went cold when the first images arrived, not metaphorically. The scientists gathered at the Vera C. Rubin Observatory Control Center in Chile actually felt the temperature drop. Air conditioning kicked in, someone noticed, but that is not why the room felt cold. The room felt cold because what was appearing on their screens should not have been possible. For decades, one rule governed modern astronomy with absolute certainty. If you wanted to see deep into space with true clarity, you had to escape Earth entirely. The atmosphere was a cage, a beautiful cage, but a cage nonetheless. Every photon traveling from distant stars had to punch through thousands of miles of air, water vapor, dust, and turbulence before reaching a ground telescope. That friction scrambled the image, softened it, blurred the finest details into statistical fog. This is exactly why Hubble was launched in 1990. This is exactly why James Webb cost $10 billion and took 25 years to build. Escape the atmosphere, leave Earth behind. Only in the vacuum of space could humanity see what the universe truly looked like. Everyone knew this. It was foundational. It was assumed. Then, on one night in June 2025, that assumption cracked. We need to establish something first before the shock lands properly. The Vera C. Rubin Observatory is not a small project. It is not a modest upgrade to existing technology. What stands on Cerro Pachón in northern Chile is the most ambitious ground-based optical telescope ever constructed. The numbers alone signal that something different was coming. An 8.4-meter primary mirror. That is nearly 3 stories of precisely curved glass designed to gather light with ruthless efficiency. Not the largest ever built, but the largest with the optical precision required for what Rubin was actually designed to do. A 3.2 billion pixel camera. Think about that number for a moment. The human eye resolves roughly 576 megapixels in the center of its visual field. This camera has nearly 6 times that resolution, recording photons across a field of view equal to 40 full moons stacked side by side. Imagine looking at the night sky and capturing the entire region around the moon, down to objects no human eye could ever perceive, in a single exposure. A 3-mirror optical design unlike anything astronomy had attempted before. Most telescopes use 2 mirrors. Rubin uses 3, each one positioned with nanometer precision to eliminate the optical distortions that have plagued ground-based astronomy since Galileo first pointed a tube at the sky. This design cost years of engineering, it cost millions in precision manufacturing, and it worked. On June 13, 2025, the Vera C. Rubin Observatory opened its eye for the first time. First light. The moment every telescope gets a single night to prove that all the engineering, all the billions in funding, all the decades of design actually function in the real world. They did not aim at something small to start. They did not aim at a single galaxy or a tight cluster. They aimed at the southern Virgo cluster, a vast region of space filled with hundreds of galaxies spanning millions of light years. They aimed wide, they aimed deep, and they aimed to see if a ground telescope could genuinely compete with what space had been delivering for 3 decades. What came back were 185 separate exposures stitched into a single mosaic that made the entire scientific community pause. The images were clean, not soft, not blurred, not degraded by the atmosphere the way every ground-based telescope had been degraded for the previous century. The detail was extraordinary. The depth was extraordinary. Galaxies that required hours of exposure time on space telescopes revealed themselves in minutes of Rubin's integration. Structures in nebulae that had only been glimpsed before now stood in full clarity. And this was just the beginning, just a test night. The equipment was still being calibrated. We need to understand what this means. For over 30 years, the assumption had calcified into absolute certainty. Space telescopes saw clearly. Ground telescopes saw through fog. The boundary was not just real, it was fundamental. Physics said it had to be. The atmosphere was chaos. Photons scattered through miles of moving air, thermal noise, water vapor absorbing wavelengths, dust particles bending light in random directions. How could any Earth-based instrument overcome that? The answer was hiding in optical physics the entire time: adaptive optics. The technology that corrects for atmospheric distortion in real time had been improving for 2 decades. Rubin did not invent it, but Rubin applied it at a scale and sophistication that transformed what ground-based astronomy could actually deliver. Thousands of measurements per second, a laser pointed at the sky creating an artificial star, mirrors that shift position thousands of times every single second, software learning the atmosphere's behavior and predicting its next distortion before it happens. All of this working in perfect synchronization to bend the incoming light back into focus before the camera records it. It worked. It actually worked. But the first light images were only the opening shock. The real revelation came in what else Rubin detected that same night. In just over 10 hours of observations, while primarily focused on the Virgo cluster, the telescope's wide field of view swept across enough sky to detect moving objects, asteroids, thousands of them. The final count from that first night reached 2,104 previously unknown asteroids, all detected and tracked and cataloged in a single evening. 7 of them were classified as near-Earth objects, asteroids with orbits that bring them close to our planet, asteroids nobody had detected before, asteroids that are now on the watch list, their trajectories being calculated, their threat profiles assessed. 7 new near-Earth asteroids discovered in one night by a ground telescope from Chile, while primarily collecting images of a distant galaxy cluster. Think about what that implies. For years, astronomers have worried about the potential for an extinction-level asteroid impact. We have detection systems, we have surveys, we have invested billions in trying to ensure that a Chicxulub-scale impactor does not sneak up on us from a blind spot in our observational coverage. And for all those years, Rubin was not even operational yet. Now it is. Every 3 days, the Vera C. Rubin Observatory will complete a full survey of the southern sky. Every 3 days, every 72 hours, the entire visible universe south of the equator will be rescanned, cataloged, analyzed for changes, threats, anomalies. Over the course of its 10-year initial survey program, Rubin will accumulate 500 petabytes of astronomical data. That is a number so large that traditional storage methods become impractical. To put that in perspective, every photograph ever taken by humanity, from the invention of the camera through this moment, totals roughly 12 petabytes. Rubin will collect 40 times that amount, 40 times all of human photography. In 10 years, 20 billion galaxies will be mapped, not photographed in tight detail like Hubble, mapped, cataloged, integrated into a 3-dimensional model of the expanding universe so complete that no previous generation of astronomers could have imagined it. 2 billion asteroids will be tracked. Nearly every potentially hazardous near-Earth object will be identified, measured, and plotted through years of orbital evolution. And because Rubin scans continuously, because it updates every 3 days, that dataset becomes something revolutionary. It becomes time-lapse astronomy. For the first time, humanity will have a cinematic view of the cosmos, not static snapshots separated by years or decades, not isolated portraits of individual objects, a living, constantly refreshing, real-time map of what the universe actually looks like. A ground telescope did what everyone assumed only space could deliver, but the images themselves deserve deeper attention because they reveal something the raw specifications could never capture. When the first Hubble images were released in 1990, they transformed public perception of the cosmos. Suddenly, galaxies were not abstract mathematical concepts, they were real, visible, structured. The Hubble Deep Field became iconic because it showed what a tiny patch of sky actually contained when you pointed a space telescope at it and waited long enough, thousands of galaxies in a region so small it would fit behind a grain of sand held at arm's length. For 3 decades, that image defined what deep space astronomy looked like. High-resolution portraits of carefully selected regions, extraordinarily detailed, scientifically invaluable, but limited in scope. Hubble could see incredibly far and incredibly deep, but it could only look at a tiny slice of the sky at any given moment. The Lagoon Nebula images from Rubin's first light represent something fundamentally different. The Lagoon Nebula is a stellar nursery roughly 6,000 light-years away, a region where new stars are being born right now, where collapsing clouds of gas and dust are igniting into fusion, where the process that created our own sun is actively unfolding somewhere in the southern sky. Hubble has photographed the Lagoon Nebula before. Beautiful images, detailed portraits of specific regions within it. Rubin's image is not a portrait, it is a landscape, a wide-field panorama showing the entire nebula in context, surrounding structures visible, the scale of the stellar nursery apparent in a way a tight photograph cannot convey, and the resolution is not compromised by that wider view. The detail is still extraordinary. Stars that would require minutes of exposure on Hubble reveal themselves in seconds of Rubin time. This is the revolution hiding inside the technical specifications. For the first time, ground-based astronomy can deliver both scale and detail simultaneously. You do not have to choose. You can see the whole structure and the finest components within it in a single observation. The Virgo cluster mosaic made this even more apparent. The Virgo cluster is not a single galaxy. It is a gathering of roughly 2,000 galaxies bound together by gravity, a structure so vast that light takes millions of years to traverse it. Mapping this cluster with Hubble would require hundreds of observations over years, each one capturing a small region, all of them needing to be stitched together manually by astronomers working from stored coordinates. Rubin captured it in 1,185 exposures stitched automatically into a single coherent image. The mosaic shows not just the bright central galaxies but the fainter satellites orbiting them, the intergalactic gas strands connecting them, the subtle structure that reveals how these thousands of systems interact gravitationally across millions of light-years. This is data density that previous astronomy could not generate, not because of technology limitations, because of time limitations. It would take space telescopes years to collect this much data on a single region. Rubin did it in hours. And here is where it becomes genuinely unsettling. The scientific community has spent decades planning for what happens when Rubin comes online. Computer models were built, data pipeline architectures were designed, teams of statisticians and software engineers prepared for the flood of information that would arrive every night. They knew the numbers. 500 petabytes over 10 years. They had prepared for it intellectually. Nothing prepared them for the reality of what that actually looks like in practice. Every night, Rubin will generate roughly 20 terabytes of raw data. That is equivalent to the entire Library of Congress repeated dozens of times, arriving every single night, 7 nights a week, 365 nights a year. The image processing happens automatically. The catalog updates happen in real time. Astronomers do not discover what Rubin found yesterday when they open their emails in the morning. Automated systems flag the discoveries immediately. The anomalies get cataloged before humans even wake up. This means something crucial. Rubin is not a telescope astronomers point at selected targets and wait for results. Rubin is a survey machine. It is constantly watching, constantly recording, constantly updating its map of the observable universe. And in doing that, it will discover things nobody was looking for. The near-Earth asteroids found on first light illustrate this perfectly. Those 7 newly detected asteroids were not the target. They were incidental. Rubin was pointed at the Virgo cluster, and while gathering light from millions of light years away, it simultaneously detected objects just millions of kilometers from Earth that had escaped every previous detection survey. What else is Rubin going to find incidentally? What if a near-Earth object was tracked for decades but cataloged as dormant? What if Rubin detects outgassing from its surface? Activity where nobody expected activity? A suddenly active threat that previous surveys had cleared as non-hazardous? What if a star we thought was static shows unexpected dimming, not the gradual dimming of a star aging, sudden dimming, the kind that would indicate something was orbiting in front of it, something big, something previously undetected? What if the asteroids showing unusual trajectories are not being pulled by gravity alone? What if their paths suggest something else is happening, something that does not fit orbital mechanics, something that demands explanation beyond current models? These are not conspiracy speculations. These are the actual search parameters Rubin's automated systems will run every single night. The questions it was specifically designed to answer, the anomalies it will flag for human review, and because Rubin updates every 3 days, because it is constantly rescanning the same regions of sky, because it will map the southern sky thousands of times over its operational lifetime, patterns will emerge that static observations could never reveal. Objects moving in unexpected ways, objects appearing where they should not exist, objects disappearing from orbits that should keep them visible, transient events that occur only once every few years, captured now because Rubin is watching all the time instead of observing scattered target regions. The automated systems will catch these, humans will review them, and some of those reviews will lead somewhere unexpected. But that is getting ahead of the immediate reality. Right now, in June 2025, the immediate reality is that a ground-based telescope has done what everyone assumed was impossible. It has achieved clarity that matches space observatories. It has delivered images of the cosmos that rival anything Hubble or James Webb have produced. It has done this while simultaneously discovering threats to Earth that had previously escaped detection, and it was not even fully calibrated yet. The Vera C. Rubin Observatory is now entering its official survey phase. The test night is over. The real work is beginning. Every 3 nights from this moment forward, the entire southern sky will be rescanned. Every transient event will be caught. Every moving object will be tracked. Every anomaly will be flagged. For the first time in human history, we have an instrument watching the cosmos continuously, not selecting targets, not pointing at chosen regions, watching. The question is not whether Rubin will find something unexpected. The question is what we are going to do when it does. The institutions have already prepared their responses. NASA has protocols. The International Astronomical Union has guidelines. There are committees in place to handle the discovery of potentially hazardous asteroids. There are procedures for announcing unexpected astronomical events to the public. Everything is organized. Everything is documented. Everything is ready, except for one thing. None of those protocols were designed for the volume of data Rubin will generate. None of those committees have actually processed what it means when discoveries arrive faster than human review can handle them. The automated systems will catch anomalies, humans will review them, but there will be a delay, a gap between detection and confirmation, a window where something genuinely dangerous could be flagged by Rubin's systems and not yet verified by a human astronomer. And in that gap, what happens if the discovery is something that demands immediate action? What if Rubin detects an asteroid on a collision course with Earth? Not in theoretical models, not in worst-case scenarios used for disaster planning, but an actual detection of an actual object with an actual trajectory heading toward impact. The automated systems flag it, the alert goes out, and then the verification process begins. How long does verification take? Days, weeks, potentially. Long enough to confirm the orbital mechanics, long enough to rule out measurement error, long enough to ensure that what was detected is real and not instrumental artifact. But how much time do we have if the asteroid is genuinely on a collision course? What if the answer is less than the verification period requires? This is not idle speculation. This is the exact scenario that keeps planetary defense specialists awake at night. A small asteroid, potentially in the 50 to 100 meter range, discovered with too little time for humanity to mount any meaningful response. Not extinction level, not Chicxulub scale, but large enough to destroy a city, large enough to kill millions, large enough that the discovery itself becomes a civilization-defining moment, because everyone on Earth will know exactly how much time remains before impact, and everyone will know that we saw it coming. Rubin will not stop there. The asteroid detection is just the beginning of what this telescope is going to reveal about the actual state of the cosmos. The 7 near-Earth objects found on first light represent objects in our immediate neighborhood, but the Virgo cluster images reveal something about the deep universe that traditional astronomy has been missing. Galaxies collide. This is not news. Astronomers have known for decades that galaxies merge, that gravitational interactions between massive systems reshape them over millions of years, that the Milky Way itself is currently in the slow process of consuming the Sagittarius dwarf elliptical galaxy. But knowing something intellectually and seeing it happening in real time are completely different experiences. The Virgo cluster mosaic shows galaxies at different stages of collision. Some systems just beginning to interact, tidal forces beginning to distort the outer regions. Others locked in close encounters, their structures already stretched and warped by gravity. Still others merged completely, their stars now mingling in hybrid structures that show the scars of the impact billions of years ago. And if you look at the timeline, if you trace the stages of collision from early encounter to complete merger, one fact becomes unavoidable. This is going to happen to the Milky Way, not immediately, not in human timescales. The Andromeda Galaxy, the Milky Way's nearest large neighbor, is currently approaching at roughly 110 kilometers per second. In roughly 4 billion years, Andromeda and the Milky Way will merge. The collision will take hundreds of millions of years to complete. The process will be gradual by human standards, but by cosmic standards, it is rapid. The images in the Virgo cluster show what that process actually looks like. Stars being torn from their original systems, entire regions of galaxies being ripped apart by tidal forces, the careful structure built over billions of years unraveling in a cosmic scale, interaction. And the sun will still exist then. The Earth will still exist. Humans, or whatever intelligence evolves from humans, will still exist in that solar system. They will witness the sky transforming. The night sky they see will change dramatically as Andromeda fills more and more of the visible heavens. The orbital dynamics of the solar system may shift. Asteroids may be dislodged. The gravitational environment Earth exists in will alter. In 4 billion years, what we think of as stable conditions will become unimaginable chaos. But that is a problem for a species 4 billion years in the future. The immediate problem is happening right now, tonight, every night that Rubin is operational. The telescope is not just mapping the cosmos, it is creating a baseline, a reference point. When Rubin scans the southern sky again in 3 days, and again 3 days after that, and again for the next 10 years, it will be measuring change. How fast are things moving? How are structures evolving? What is happening in the universe between observation intervals? For bright objects, for nearby asteroids, for stars in our galaxy, that change will be noticeable, measurable, real. Rubin will catch motion that previous static observations missed entirely. It will catch objects that appear and disappear. It will catch events that occur so quickly or so subtly that only continuous observation could reveal them. And because the data is processed automatically, because anomalies are flagged immediately, because the entire system is designed to catch the unexpected, Rubin will find things that were actively being hidden by the limitations of previous astronomy. The question is whether those things are the discoveries science wants to make. The Vera C. Rubin Observatory is not just a bigger telescope, it is not just a better telescope. It is a fundamentally different approach to how humanity observes the cosmos. It replaces the model of astronomers carefully selecting targets with the model of constant, unfiltered watching. It replaces isolated discoveries separated by months or years with a continuous stream of data, revealing the actual moment-to-moment state of universe, and in doing that, it changes what we are actually allowed to discover. For decades, the limitation was technological. We could not see deep enough, we could not see wide enough, we could not process the data fast enough. All of that is solved now. All of those excuses are gone. What remains is the question that nobody is asking in the scientific community right now, but will eventually have to ask. If Rubin finds something that contradicts fundamental assumptions about the cosmos, something that does not fit into existing models, something that demands explanation beyond current physics, what do we do with that discovery? Do we announce it? Do we bury it pending review? Do we wait for confirmation that might take years? Do we present partial findings that might create panic? The protocols say we announce discoveries. The committees say we follow procedure. The guidelines say we maintain scientific integrity. But the guidelines were written before Rubin existed, before we had a telescope that could find things we were not looking for, before we had a system designed to catch exactly what we were trying to avoid seeing. The first light images are beautiful. They are scientifically groundbreaking. They prove that ground-based astronomy can compete with space telescopes. They demonstrate that the era of static snapshots is truly over. But they are also a warning. Rubin is now watching, and in the southern sky, in the cosmic territory south of the equator, nothing will move without being observed. Nothing will change without being recorded. Nothing will happen without being entered into a database that grows by 20 terabytes every single night. The universe is no longer unknown territory. It is becoming known, and that knowledge is arriving faster than we are prepared to process it.